Hello, everybody. Get things going. Let's see, attendance. Sorry. There's the attendance form. Please, fill it out as usual. There's again. Let's see. So I feel like we should continue talking about systems of differential equations, linear differential equations. The light here just seems. I don't love the light in this room. I need to get one of those ring things to light me up. Anyway, not your guys' problem. So I think we should continue talking about that, but I should throw it out there. Are there any questions or do you guys want to see any more examples about double integration? Like, should we do a little more of that or should we move on? Who votes yay? Yes. Who wants to see some double integration still? Yes? Okay. Specifically, I'm imagining ones where we still change the limits of like the order of integration. Yeah, those are usually the ones. Okay. We'll do one or two of those, and then we'll move on to differential equations, and we'll talk about classifying solutions. We'll also talk about the compartment diagram, which is pretty straightforward, but you can it's not too bad. And then we will move on to like complex solution, complex eigenvalues, and what that kind of means for us. So let's see. I'm trying to remember which one we did. I don't think we did this one. Let's look at this. Just the integral from 0 to 8, and then from q root of y to 2 of dy dx over y to the 4th plus 1. Just written kind of weird. I would probably, so this is from another textbook I have. I would probably write the integral, I would probably rewrite it as 1 over y to the 4th plus 1 dy dx. And as we typically see here, this thing that we're trying to integrate can't be integrated. Right? There's no nice way of anti-differentiating 1 over y to the 4th plus 1. It just doesn't work. So we have to draw the region. And again, you can totally use Desmos for something like this. I'm going to draw. So actually, I'm actually curious. Let's look at Desmos for a second because it might not be super easy. So let's take a look at Desmos for 1 sec to see if it is easy to draw this. Grab Desmos here. Share my screen. Yeah. So if I want to graph x equal to the cube root of y, so that's x equal to y to the 1/3. Oops, that's, oh, come on. I'm sorry, I'm trying to type things the wrong way. Yeah, that doesn't actually, no, that's right. Yeah, because that's y equals x cubed. So you can totally do that. You can totally graph x as a function of y, and it'll work out nicely for you. And then we might as well do the other one, just to kind of see where it's at. X equals 2. No, sorry, y equals, x equals 2. Right, so we can see that we definitely have, our region. Sorry, I'm trying to like point at things on my computer. Sorry, so here we have our region. We're going from x equal to this function to x equal to this function. And then we're going as low as y equals 0, which is right here, all the way up to y equals 8. So we're just describing the region in here. And now we're going to switch it around. And so we're going to take that region, now I might as well draw it. So yeah, Desmos is great. So right, here's the region. And instead of doing horizontal cross sections like we were doing it written this way, now we're going to use vertical cross sections. So our bounds are going to be, the lower bound is going to be y equals 0. The upper bound is going to be x equal to the cube root of y, which becomes x cubed equal to y. That's y equal to x cubed. And then our strip is going to slide as far left as x equals 0, as far right as x equals 2. So we're going to rewrite our integral as the integral where x goes from 0 to 2, and y goes from 0 to x cubed of 1 over y to the 4th plus 1 dx dy. And a lot of times the way these work out is once you do this change, then once you do the integration, you're going to get a nice u substitution. Right, so if I integrate this, you get the integral from 0 to 2 of x times this constant. X, I'm integrating with respect to x from 0 to x cubed. I feel like I'm making an error somewhere. Let me look at one thing real quick, sorry. I made a small mistake. How do I want to fix this? Yeah, I made a dumb mistake. I'm sorry. So here's what I did. And I actually didn't listen to my own kind of words of wisdom from last time, which is that if you have variables here, this should be the opposite of that, right? The variable here and the thing you're integrating with respect to first shouldn't be the same. This actually should have been the cube root of x. Sorry. So our region isn't right. Let's redraw it. Because it really should have been y equals this to y equals this, and then x equals this to x equals this. It's actually just going to look like this thing kind of rotated around. So what we really have, so here's how I knew I had made a mistake, right? I was getting to here, but I was having to plug in, right, because I integrated with respect to x, I was going to be having to plug in 0 and x cubed for x, which is wrong. Right? You shouldn't be plugging in the same variable to that variable. So what I really should have had was so I have y equals the cube root of x. Looks like this. So y equals 2. And then x goes from 0 to 8. So I'm looking at this region here. And then I'm going to flip it around. So instead of doing y equals this to y equals this, I am going to draw a horizontal strip and go from as far left as x equals 0 to as far right as, instead of y equals cube root of x, it's going to be x equal to y cubed. So that's what this region should, and then what the y's are from 0 to 2. So this actually should have been a y cubed up here. And then you're going to still integrate the same way, right? Integral of this with respect to x is still just x times all that. But now, y cubed. And then when we plug in y cubed for x, we get, from 0 to 2 of y cubed times 1 over y to the 4th plus 1. And then we plug in 0, we get 0. And now we've got a great u substitution, right? We can just let u equal the bottom, du is essentially going to be at the top. So here, we could let u equal y to the 4th plus 1. Our du is 4y cubed dy. I have a y cubed dy, so I'm going to say 1/4 du. 1/4 du is equal to y cubed dy. So this integral becomes the integral, so my y cubed dy is my 1/4 du over u. And personally, I'm a fan of changing the limits of integration. So instead of saying I have y equals 0 and y equals 2, well, if y equals 0, u is going to be 0 to the 4th plus 1. And if y equals 2, u is going to be 2 to the 4th plus 1, which is 17. And then we don't have to change it back to y's. So you get 1/4 natural log of the absolute value of u from 1 to 17. You plug in 17, and you get 1/4 the natural log of 17. Minus 1/4 the natural log of 1, but that's just 0. So that's how you do one like this. Most of these ones where you have to switch to the order of integration, once you do the switch, the integral that you have to actually do, like the second half of it, is usually pretty straightforward. It's usually a nice U sub, or things cancel out, or something like that. Let's see. Let's see if I've got another good one, and then we'll move on. I don't like you. So here's a good one that's good for other reasons. So I'm not sure, I imagine, I mean, this one, it's in the book, it shouldn't be too terrible. I hope we'll give me the instruction. Sorry, I have to think about this for a second. No, I feel like that's gonna suck. I don't want to do that. Never mind, not that one. I guess we could do. Sorry, I thought I had one all picked up here. Now I'm like, sure, let's do this one. Okay, before I go any further, what should my first d here be? Should it be dy or dx? And I know that because I have an x here, so I should have a dy here. Right, because really, when I'm looking at this part here, this is y equal to x and y equal to 2. Meaning the inner integral is integration with respect to y, because my limits of integration are y things. But then we're going to switch it up. So here, I want you guys to go ahead and draw the region of integration. Shouldn't be too terrible. You're drawing y equals x and y equals 2, and then you're going from 0 to 2 for the x's. Ah, man, got pedal over my hand. Terrible. So there's our region. It's a triangle. And the way it's written currently, we're using vertical strips, right? We're thinking of our vertical rectangles as being bounded below by y equals x and above by y equals 2, and then moving as far left as x equals 0, and as far right as x equals 2. But we're going to switch it, right? That's the whole point. So now we're going to use a horizontal rectangle. And we're thinking that the right-hand boundary is x equal to y, the left-hand boundary is x equal to 0. So those are inner limits of integration. And then our outer limits of integration are going to be, well, how far up and down? This can go as far down as 0, as far up as 2. So that's what we're going to get. I guess I really want to make sure I emphasize here, the best way to find the new limits of integration, right, to change the order of integration is just to draw the region. Like there really isn't a better way to do it. And I will also say, it's it's maybe not impossible, but it's pretty hard to do without drawing the region. So you guys really should draw the region if you can. And again, you've got Desmos, you've got other graphing utilities, so draw the region if you're changing the order of integration. It's just the only way to do it, really. So now I'm going to integrate this with respect to x. So let's see. So the integral, so this is a constant, so it's just going to hang out. So I get the integral of sine of xy. So I know the integral of sine of x is just negative cosine of x. What's the integral of sine of xy? Let me ask you a different question before you answer. What's the integral of sine of 4x? What is the integral of sine of 4x? That's a good question. Well, it's something like negative cosine. It's negative cosine of 4x. Almost. But if it was negative cosine of 4x, well, the derivative of negative cosine of 4x is positive sine of 4x times 4 because of the chain rule. So to account for the chain rule that would happen, we have to divide by 4 or divide by that coefficient of x. In a similar way, the antiderivative of sine of xy is going to be negative cosine of xy divided by y. Interesting. And then one of these y's cancel. I will point out, because it just occurred to me, we totally could have done this without changing the order of integration, but if we wanted to, we would have had to do integration by parts twice. Right, because we would have had it could have done it tabularly, right? That's totally something we could have done, but we don't want to do that. So then this is going to be the integral. Oh, sorry, I forgot one thing. Forgot to that, right? Yeah, we could have done that thing. I was just double checking here. Yeah, we totally could have done that integration by parts. It's probably not the right way to go, but it's totally we could have done. So then, plugging in y for x, I get the integral from 0 to 2 of, let's see, 2y times, let's bring out the negative sign. So you get negative 2y cosine of y times y. And then minus, now usually when you plug in 0, you just get 0. That's not the case here. When I plug in 0 for x, I'm going to get cosine of 0, which is 1. So we get 2y times 1. So we get a minus 2y. Not quite as nice as the other ones. And that is right? Because if I hadn't factored out the minus sign, it would have been minus 2y times cosine of y times y. The minus minus would have been a plus. Okay, this is terrible. I don't really want to do the rest of this, but I will. So here's what I see. I see that 2y is exactly the derivative of y squared. So that the integral of cosine of y squared times 2y is just sine of y squared. I did the u substitution, right? I said, oh, u is y squared, du is 2y. I have cosine of u, the antiderivative is sine of u, which is sine of y squared. And then I've got this minus sign still in front. And then the antiderivative of 2y is just y squared. So I end up with negative sine of 4 minus 4 minus sine of 0 minus 0, which is 0 over here. So my answer ends up being negative sine of 4 plus 4, or I would write it as 4 minus sine of 4. Which isn't a very nice looking answer because sine of 4 is weird, but it is an answer. All right, 2 things to say one more time. Thing 1, double integrals. When you change the order of integration, you got to draw the region. Thing 2, double integrals. When you change the order of integration, it should make it so the integral is, well, I should say, if you're changing the order of integration, it's usually because the thing you're trying to integrate is terrible or impossible as is. This one's not quite impossible, but it is terrible. And then what should typically happen if the problem has been written well is that the thing you're integrating should get nicer, right? This 2y cosine y squared is much nicer than 2y squared sine of xy because it's a nice u substitution. If you see something becoming a nice u sub, that's usually a good sign. Whereas this would be terrible integration by parts twice. Okay, so sorry, one second. Socks coming off. All right, let's continue on with our systems of linear differential equations. And so I kind of want to give you guys, well, I want to give you guys a lot of things, but there's some big picture stuff I want to say. So let me look over here real quick. And I'm starting to forget which ones we've done, which is too bad. It's all right. Let's just look at this one. I can make them different numbers. So let's say we have this linear system of differential equations. D x dt is equal to 5x, and dy dt is equal to 3x plus 2y, which ends up having this matrix, which we're happy about, because when our matrix looks like this, we don't have to do any work to find the eigenvalues. The eigenvalues are just the diagonal entries. And maybe we'll find that. Yeah, we'll find that. So here's what I want to say. Just right now, having done only this work, we know that 0, 0 is an unstable equilibrium. Specifically, it's a source where all of the arrows in the direction field emanate out away from it. But there's more to say about this. So let's actually solve the system, because I want to show you guys this. So we're going to find the eigenvectors. It shouldn't be too terrible. So first eigenvector, we're doing, for lambda 1 equal to 5, we have the matrix. Whoops, that's not how you write that there. Times the eigenvector, which we're going to find. And let's not call it x and y since I'm using x and y. Let's call it like u1, u2 equal to 5 times u1 and u2. And you can see here that the first row is going to tell you nothing, because you're going to have 5 times u1 plus 0 times u2 equals 5 times u1. 5 times u1 equal to 5 times u1 is true, but not informative. Looking at the second row, I have 3 times u1 plus 2 times u2 equal to 5 times u2. And subtracting through the 2 for u2 here, I have 3u1 equal to 3u2, which means u1 equals u2. So it looks like my eigenvector is going to be 1, 1. Okay. So now let's look at the other eigenvalue. Lambda 2 equal to 2. So that's where I've got the matrix 5, 0, 3, 2 times. And again, I'm going to call it u1, u2 equal to 2 times u1, u2. And we end up getting 5 times u1 equals 2 times u1. Which means that u1 equals 0. Right? There's no other choice. And once you know that one of the parts of the eigenvector is 0, the other part is any non-zero number you want to pick. We're always going to pick 1. So our eigenvector here is 0, 1. Okay. So here's what our solution to this system looks like. So our solution, which again, I would probably encourage you to memorize this next thing I'm going to say. The solution, right, is C1e to the lambda 1t v1 plus C2e to the lambda 2t v2. Now you're going to see this a whole lot. So in this case, our solution is just, right, xy equals to C1 e to the 5t times v1, which is, where'd you go? 1, 1. Plus c2 e to the 2t times v2. And yeah, I'm gonna erase a little more because I want to still stay on this side of the board for a second. So we don't need this, we don't need this, sure. So you can actually kind of see why it's unstable if you look at x and y and what they're actually equal to. So looking at what x is equal to, right? X is just the first component, so x, or x of t if you like, is equal to c1 e to the 5t times 1 plus c2 e to the 2t times 0. So it's just that. And y of t is equal to c1 e to the 5t times 1 plus c2 e to the 2t times 1. And here's the idea here. The reason why these solutions are unstable, because their eigenvalues are positive, is because as t gets larger and larger, x is going to get larger and larger, and y is going to get larger and larger. So that's kind of what's happening, right? If you think about the graph of x versus time, you're starting at some initial value like c1, and no, I think you have to get larger. Maybe C1 is negative to start at. No, I don't think so. I'm just trying to think, could C1 be negative? Does it even matter? Either way, if C1's positive or negative, you're still going to eventually like do that, right? You're going to get really, really big. And the same thing is going to happen for Y, right? If you're graphing Y as a function of time and you're starting at C1 plus C2, whatever that is, also gets really, really big. So because these eigenvalues are positive, as time gets larger, the value of x and the value of y both get larger and larger and larger. They don't get close to any one particular value. They're unstable. Let me see if I've got this.
Would we be ever asked if for 3 lambda values?
I don't believe so. That is typically not within the scope of this course. It is certainly something that is very doable in linear algebra. You can definitely have a 3x3 matrix and find this. So basically, whatever the size of your matrix is the number of eigenvalues you can find. So if it's 3x3, you can find 3. If it's 4x4, you can find 4. It just, the math becomes much more difficult as the matrix is larger. And we can look back at p-plane for a second if you want to kind of see what this looks like. So for this equation, I've got dx dt equals 5x. And dy dt equals 3x plus 2y. And sorry, I should share my screen. And so, wow, I've got tons of things. Sorry, that's not what I wanted. Let's show what I wanted was this. And if I graph this, right, you can see, okay, again, here's my origin at 0, 0. And everything is moving outward from it, right? So that's a source. And again, we can look, right? The eigenvectors are 0, 1, and 1, 1. So if we pick something at 0, 1, if I click it right on, it should just go straight up. Close enough, right? That's the eigenline, right? We're just going in the direction of the eigenvector. But as soon as you're off of the eigenline just a little bit, right, things really go different directions. 1, 1 is also an eigenvector. So if I try and hit 1, 1 here, oh, I know it. So if I go 1, 1, sorry, my scale is kind of weird. That's 1, 1, which doesn't look like 1, 1. Right, we're definitely in the straight direction of the eigenvector. Whereas if we go, off a little bit, other things happen. Woo, fun times. So that's kind of what's happening, right? But everything is going away from the origin. Yeah. And then what I want to say, yeah, is it's different if you have a saddle. And I know we talked about saddle. So let me just do 2 other real quick examples. So I'm not going to do the solution. I'm just going to show you, kind of how. So if both of our eigenvalues are negative, so if lambda 1 and lambda 2 are both negative, then our solutions look like, oh, sorry, let me stop sharing my screen. And so if lambda 1 and lambda are both negative, then our solutions still look like, xy equals c1 e to the lambda 1t plus, v1 plus c2 e to the lambda 2t v2, which if I write this way. Right, I think of V1 as V11 and V, I guess 1, 2. And V2 as V21 and V22. Then the X values is C1 e to the lambda 1 t V11 plus C2 e to the lambda 2 t V21. And the Y values in a similar way are C1 e to the lambda 1 t V12 plus C2 e to the lambda 2 t V22. And here's what I want you to know. If both of these lambdas are negative, then as t gets larger and larger, well, e to the lambda t is going to get smaller and smaller and smaller, right? You've got like e to the negative 5t. That gets super duper small as t gets larger. Same thing for all of these. So what we've got happening here is something different, right? If you're graphing x as a function of time, well, you're starting at some initial value, but then as time goes on, the values get really, really small. And the same thing is true for y. And it's even true if one of the eigenvalues is positive and one of the eigenvalues is negative. So if you have, say, lambda 1 being positive and lambda 2 being negative, oh, sorry, I said the wrong thing. If this were the case, you wouldn't have this. Sorry, I misspoke. Let's say this over here. You'd be back in the previous kind of situation. Right? If lambda 1 is positive and lambda 2 is negative. So right, if we have a saddle is also unstable. Right? Any point except for a point on the right eigenvector is going to blow up. So we still have the same sort of thing, that both x and y are doing this sort of thing where they're getting larger and larger and larger, because again, this term where lambda is positive is going to blow up. The one exception is if you happen to be on the eigenvector for the eigenvalue that's negative. So if our initial conditions were such that C1 was 0 and C2 was whatever, not 0, then this wouldn't contribute, and that being positive wouldn't do anything. So saddles are also unstable unless you happen to be on the eigenvector that goes with the negative eigenvalue. Okay, so let me grab some things here. Try one sec. Okay, so so I think I've said it enough times. Let me show it to you one more time. So, let me grab the attendance bar one more time. Here's the attendance in case you haven't gotten it. And so I'm looking at this. I think Grant has a lot of great things. I use this stuff all the time. So let me share here. Let me close this. So I'm looking at this page over here, which says, right, if you've got one one's negative, one's positive, we have a saddle, and you've got this kind of behavior where along one eigenvector you're going towards the equilibrium, along the other eigenvector you're going away from the equilibrium. So if you start somewhere like over here, right, that's my initial condition right there, then I'm getting pushed kind of in this direction, but then as I get closer to the other eigenvector, I'm getting pushed away in that direction. And then here are the behaviors of x and y, right? They both eventually get larger and larger and larger. If both lambdas are negative, we have a sink, just like when they're opposite signs, we have a saddle. And here, no matter where we start, both eigenvectors are pushing us towards the origin, right? Starting here, we're getting pushed, down to the left and down to the right, we're getting pushed right there. And the same thing if we start here, we're getting pushed that way. So that's a sink. And then lastly, if both eigenvalues are positive, those are both pushing us away from the origin. So if we start somewhere like here, we're getting pushed, up to the left and up to the right. And so we're eventually kind of going up, and away that way. So I would encourage you guys, to maybe, if you want, where's the chat here? Whenever I share my screen, I always lose the chat because there we go. Awesome. So there's that particular document if you want to look at it yourself. But Grant's webpage has lots of great stuff. But what I want to say now is, let me stop here. Yeah. So there are lots of, different systems we can look at. And basically, whether or not you have a sink, a source, or a saddle point, all comes down to just whether the eigenvalues are both positive, both negative, or one positive and one negative. It doesn't matter if they're nice integer numbers or they can be irrational as well. So what can also happen though is we can have something like, let me go to the next one here. Sure. We can have something like this. I kind of like this to be slightly different. Let me see if I can make this just a little bit different. Sorry, I'm trying to change it up just a tiny bit. If I want to fix that, I want it to be a 2. Okay, let's say we have this matrix. So I have this matrix. Now, when I say I talk about compartment models, sorry, so we'll do this example. Yeah, we'll see. So this is corresponding to, right? This means I have the system dx dt equals 0x minus 2y and dy dt equals x plus y. Right, so a lot of times people just like, oh, here's the matrix. We know the system it came from. So now I'm going to find the eigenvalues. So I'm going to take the determinant of 0 minus lambda minus 2, 1 minus lambda. Let's see, what do I get here? Negative lambda times 1 minus lambda minus negative 2 minus 1. Sorry, negative 2 times 1. Which ends up being, let's see, negative positive lambda squared minus lambda plus 2. And don't fool yourself into thinking this one factors. It does not factor, right? There's no way to multiply the positive 2 and add it to negative 1. So we have to appeal to the quadratic formula. Here's what's going to happen. Here's the quadratic formula. We get lambda equal to negative b plus or minus the square root of b squared minus 4 times a times c. Sorry, I should actually write what those are. B squared times 4 times 1 times 2, all over 2 times a. That ends up being 1 plus or minus the square root of 1 minus 8, which is negative 7, which is imaginary. And this is, if I write it as the real part plus or minus the imaginary part, it's 1/2 plus or minus the square root of negative 7 over 2, which is I times the square root of 7 over 2. So this is the real part. This is the imaginary part. So here's the nice thing about this. We can still look at the real part to know something. So just like before, if both eigenvalues were positive, we had an unstable source. Here, both eigenvalues having a positive real part mean it's also going to be unstable. But it's not going to be a source anymore. It's actually what's going to be called an unstable spiral. And here's why. Yeah, we got time. We got enough time to say this. So how do I want to explain this? So yeah, sorry, I don't see what I want to say here. Did we do this? So we're not going to find the eigenvectors, but we're going to pretend like we did. The solution's still going to be the same. So the solution would still be, xy equal to c1 e to the lambda 1 t v1 plus c2 e to the lambda 2 t v2, where lambda 1 is one of the eigenvalues, 1/2 plus and lambda 2 is equal to 1/2 minus 7/2. So if that's what's going in here, and that's what's going in here, well, here's the thing. There's this thing about having e to a complex number. And I don't know if you guys have seen this before, but it's worth knowing. So there's this thing, it's called Euler's formula. It says e to the I times theta is cosine theta plus I times sine theta. And there's a way to show this using Taylor polynomials. I don't want to bore you with all the details, but let me just show you. So if you look at what we've got over here, e to the I theta is cosine theta plus I sine theta. And one way you can show is by using Taylor polynomials. I don't remember, did we do Taylor polynomials in 17a? We did? Okay. So there's a Taylor polynomial for sine of x. It's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, etc. There's one for cosine. It's essentially the same as sine, but with even powers. It's 1 minus x squared over 2 factorial, etc. And then e to the x is kind of the combo of them both. It's 1, but they're all positive. 1 plus x squared over 2 factorial plus x equals 3 factorial, etc., etc., etc. So then e to the, instead of x, e to the I theta is 1 plus I theta instead of x, plus I theta squared instead of x squared over 2 factorial, plus I theta cubed over 3 factorial, etc. But the i's are the imaginary numbers I. And so I squared is just -1. And I cubed is just I squared times I, which is -1 times I. And so this ends up becoming 1 plus I theta minus theta squared over 2 factorial minus I theta cubed over 3 factorial, etc. And it exactly breaks up into the even parts that look like the cosine and the odd parts that look like the sine with an I factored out. And so it exactly is cosine theta plus I sine theta. And if, I know I went over that pretty fast. If you didn't catch all of it, it's not that big a deal. The point is that I can take e to the this, right, e to the 1/2 plus I times root 7 over 2, and write it as, sorry, I always get a little bit, it's e to the 1/2 times e to the I times root 7 over 2. And this part here, sorry, and there's a t I'm forgetting about, apologies. Sorry, this is getting a little bit wacky. So this is e to the 1/2 t times e to the this, which this part's going to become, well, this is like e to the I theta. This is going to be like cosine of my theta, which is root 7 over 2t, plus I times sine of my theta. Okay, here's the whole point. If you're thinking about what's happening to all this as t gets really, really big, well, e to the 1/2 t is going to blow up. And all of this, as t gets bigger and bigger, this is just going to make you oscillate, right? As t gets larger, cosine t plus I sine t is just going to kind of make you go wavy. And if we look at this next page here, that's exactly what's happening. So if you have something like we have here where our eigenvalues are both have positive real parts, right? Like here, we're saying alpha is the real part and alpha is greater than 0. We have this outward spiral, and what's happening with x and y is they're both getting larger and larger, sorry, or x1 and x2 or x and y, but they're oscillating back and forth because of this part right here. It's making us oscillate. And if we look at the actual p-plane for this particular example, if I look at dx dt equal to minus 2y and dy dt equal to, what do we got there, x plus y. You can see we have this outward spiral, right? It's spiraling out. I mean, how can let me say it one more time. It's spiraling outwards. It's an outward spiral. So the things to notice that are the same are is if the, how do I say this? If the real parts are positive, whether they're whether it's totally real or imaginary, right? If the real parts are positive, it's going to be unstable. If they're both just real positive numbers, it's a source. But if they're both imaginary numbers where the real part's positive, then it's an outward spiral. And then we also have if both of them are negative, right? If they're real and both negative, we have a sink. But if they're imaginary where the real parts are negative, we have an inward spiral. So sorry, one more. So these eigenvalues, these correspond to an outward spiral, unstable. But if, for example, and I'm just going to make something up, if our eigenvalues were, say, I don't know, -2 plus or minus 3i, where the real part is negative, then this would be an inward spiral, which would be stable. And the last thing that can happen is that you can have a purely imaginary eigenvalue. So if you had eigenvalues that were like 0 plus or minus 3i, well, then you don't have any growth or decay, right? You don't have e to the 1/2 t getting larger or e to the 1/2 t getting smaller, right? You don't have this or this. You have e to the 0t, and that's just going to make it not get bigger or smaller. So you're going to have just a neutral spiral where you just keep circulating around and around and around, which, I mean, looks like what Grant has drawn here. It looks like this, right? Where you have oscillation for both x and t, but there's not a growing oscillation or a decaying oscillation. It's just an oscillation. And so in the plane, it's going to look like you're just circling around and around and around. And do I have, so let's look at this example he's given down here, where the matrix was 2, -3, 5, -2. If we look at this one, where the eigenvalues were both purely imaginary, and I know we didn't find them, but they are there, 2x minus 3y, and then 5x minus 2y. We graph this one. So it's not super easy to tell just looking at the direction field that it's going to be a neutral spiral. You definitely need the eigenvalues. You need to know that they're both 0 plus or minus I√11. But if we click a place on the phase plane, we can see, oh, we're not spiraling in or out. We are literally going in just a loop over and over again. So that's a neutral spiral. And that's pretty much the list of the 6 things that can happen. If your eigenvalues are purely, if they're real, if they're both positive, it's a source. If they're both negative, it's a sink. If one's positive, one's negative, it's a saddle. And then if your eigenvalues are complex, if the real part's positive, you have an outward spiral. If the real part's negative, you have an inward spiral. And if the real part's 0, you have a neutral spiral. And you can't have the real part be opposite signs, right? And blah, blah, blah. The solution to the quadratic formula is always going to be something plus or minus this other part, and the other part's the imaginary part. So it's always going to be positive number plus or minus imaginary number, or negative number plus or minus negative number. It can't be one positive, one negative real part. So those are the 6 things that can happen. And let me go ahead and you can find all this stuff on Grant's website on the old 17C stuff. But here's a link to that one as well in case you want to look at it on your own. I know we didn't talk about compartment diagrams. They're not too terrible. I can definitely do an example of that on Monday. Or I can even make it. I'll make a compartment diagram video because it's not too terrible, but it is nice to see it. at least one time. So I'll make a video of that sometime today and post it in case you guys have questions about the compartment diagram question, but it's really not too terrible. But that's for me to remember to do later. I think that's it. I don't think, right? So does anyone have, there aren't any more midterms, right? Everyone's had their midterm that's having a midterm. And no one has a second midterm, right? There's just a final in our distant future. Is there a second midterm?
I believe Rodmacher has one more midterm.
Oh, he does? Let me double check on that because I know I wrote them down. Let's see. Oh, he does. So Rodmacher does have a midterm in 3 weeks from today. Okay. Well, we'll prepare for that, but yeah, Carlson does have one in like 2 weeks on the 14th. That seems like a weird day to have it, but okay. So anyway, so yeah, so there are a couple more midterms for both of you guys that don't have Rodriguez, but all of you that don't have Rodriguez. And yeah, we'll continue talking about this stuff. Let me know if you have questions. Feel free to post a discussion in Canvas or send me an email, and I will try to do whatever you want me to do. All right. Have a good weekend, everybody, and I'll see you all on Monday.
Thank you.
You're very welcome. Always.
Thank you.
Yep, no problem. Good seeing you guys.